So we've talked a little bit about the idea that you can, by starting with the potential, figure out what the force is by operating on the potential with the gradient operator, or in other words, by taking the partial derivative with respect to x, multiplied by I hat, partial derivative with respect to y, multiplied by j hat, partial with respect to z, multiplied by k hat, with appropriate negative signs involved. And we've sort of talked a little bit about both the idea that operationally the way that you take a partial derivative in Cartesian coordinates is to hold the other variables constant and take the partial with respect to, actually the way you take a partial derivative in general, is you hold the other variables constant and then take a derivative with respect to the thing that you're interested in. So we did this one example, and we looked a little bit at ways to sort of think about what a partial derivative means when you've got a function of multiple variables, and that was what that MATLAB video was. So in this video, I want to do one more example of sort of how you can do this, and I thought a useful example for that is actually to use gravitational potential for the case where you're actually in the longer range situation. So for the case where you've got like a satellite that's located some distance r away from the Earth's surface, right? So the satellite is located at some position vector r, and we're interested in knowing what the force is on the satellite. Now you know what the answer is there, right? The force that the satellite feels is going to be in the minus r, in the r hat direction, right? It's going to be a negative force, and it's going to be a g times m1 times m2 over r squared, right? That's what we actually know that the answer is. We also know what the potential energy is, right? When you talk about what the potential energy is of gravitational field, the convention is that you take that potential to be 0 out at infinity, so that as you get closer and closer to the other object, the potential energy becomes more and more negative, which is a way of saying that it takes work to pull the object from being close to the other object to a long ways away. So the potential energy is minus g m1 m2 over r. And this is actually over the magnitude of r. So let's just see if we can use this formalism of taking the partial derivatives in order to go from this potential to this force. And I'm going to do this in Cartesian coordinates, not because it's the best way to do it. In fact, it's a terrible way to do it, but because it doesn't require us to introduce any more issues having to do with the gradient operator. So if I write my potential energy in terms of x, y, and z, right? My potential energy in terms of x, y, and z is g m1 m2 over the square root of x squared plus y squared plus z squared, and of course I have this negative sign here, right? This is how far I am away from the origin, right? So I'm going to choose my origin to be at the center of the Earth. So my potential energy is gets closer and closer to 0 the further away I get from the origin. Okay. When I try to figure out what the force is from this, the force that this is going to exert is going to be minus the gradient of the potential energy, which is going to be minus the partial with respect to x of the potential in the I hat direction, plus minus the potential with respect to y of the potential in the j hat direction, plus negative partial with respect to z of the potential in the k hat direction. Okay. And we can do this. Why don't we do this first term? So I want to take partial with respect to x with a negative sign of the quantity minus g m1 m2 times x squared plus y squared plus z squared to the minus 1/2 power, right? And when I do that, not surprisingly, I'm going to treat y and z as if they're constants. And so let's get rid of, well, first of all, get rid of those two negative signs. I'm going to pull down a negative 1/2, right? So this thing is going to give me minus 1/2 g m1 m2 times x squared plus y squared plus z squared to the minus 3/2 power. But then I need to chain rule this, and so I'm going to also pick up a factor of 2 times x from the x squared, right? So the partial, that gives me minus the partial with respect to x of the potential is x times g m1, oh boy, I made a mess of that. So it's x, so g m1 m2 times x, all divided by x squared plus y squared plus z squared to the 3/2 power. Okay. Clearly, if I do the same thing with respect to and I lost a negative sign here. I've got one more negative sign. If I do the same thing with respect to y, the only thing that'll change is I'll get a y here. If I do the same thing with respect to z, the only thing that'll change is I'll get a z here. So we could actually go ahead and write out what the full force is going to be for this. So my force ends up being minus g m1 m2 divided by x squared plus y squared plus z squared to the 3/2 power times the quantity xi hat plus yj hat plus zk hat. Okay, and just to remind you where that came from, the first term is going to be the partial with respect to x of the potential times I hat. So that's where this xi hat term is going to come from, and all this stuff out front is just this term here, right? And I'll get the same thing for the d by dy term, and the same thing for the partial with respect to z term, except for I'll pick up a y and a z right here. Okay, so that's what my force ends up being. Of course, we can recognize that this quantity is simply r vector, right? This quantity is the magnitude of r vector cubed, right? And so I could rewrite this as minus g m1 m2 divided by the magnitude of r vector squared times r vector divided by the magnitude of r vector, right? Because r vector squared times this, r cubed is r squared times r. This is r. So this quantity, of course, is r hat. And so not surprising, I get a force that's g times m1 times m2 over r squared in the r hat direction. And now I'll just write QED because it's always nice to use a little bit of Latin. But the point of this video is purely just to sort of walk through an example of actually doing these partial derivatives and showing you that you actually get the force by taking the partial derivatives of the potential.